Hello everyone, I'm so glad to be here to present you my presentation, Platform Engineering on AWS infused with AI, here at Cloud Native Zurich 2025. Thank you so much for Milena, Phil, and Tom for having me here. This is a re-recording of my speak at Cloud Native Zurich because there were some Wi-Fi issues, and here I am doing again a recording so that you can see that in good quality and with all the demos working. My name is Kuendig. I'm the CTO at CodeBit, an AWS Advanced Consulting partner based in Zurich. I'm also an AWS ambassador. That's a designation from AWS that was awarded globally to roughly 300 people. What is all the buzz about platform engineering? What is it all about? It's really about giving the developers full freedom to deploy their applications and microservices on a well-secured platform and stay within company policy. So what is platform engineering? So with platform engineering, when you go into the cloud, use Kubernetes, it really becomes complex. These are not easy solutions. They require a lot of know-how to be able to operate in a cloud or on Kubernetes. So there is quite a bit of complexity coming out from the bottom, from the infrastructure part, and we want to manage that. We want to be able to manage that complexity in a way that we can make it very easy to consume for the developers and the product and service teams so that they can consume these services from the platform, from the infrastructure below in a way that is Kubernetes native, so that they can use reusable components, platform services, know-hows as golden path and consume them as a service with simple API calls. The platform team is actually providing that. They are abstracting the complexity away so that the developers can really easy consume these services. How is that in the context of a platform built on AWS? Here you see an example of how we could do that. So we have split that up in multiple panes, and these multiple panes are structured in a resource pane. So in the resource pane, we use, of course, Kubernetes that we run on a fully managed Kubernetes service from AWS called EKS. Then, of course, we need databases. With databases, we can have MySQL, Postgres, DocumentDB, DynamoDB, or GraphQL databases fully managed from AWS. For example, MySQL or Postgres can be run on Aurora Serverless v2 in a fully elastic way. Then we need great networking, so with VPCs and transit gateways and Route 53 services, so that the resources on top of it can really easily consume and run on that networking. Then we need quite a few security services that we are going to deploy for certificates, for keys, for secrets. All of these things are coming out of the AWS platform very easily and make the platform much more secure. In monitoring and logging, we use CloudWatch, Grafana, Prometheus, and other solutions to provide good observability and tracing for metrics and logs for the whole platform, for all the applications. The middle, that's the heart of all of it. So of course we run Kubernetes, and that's a platform orchestrator, and the platform orchestrator hosts a couple of solutions so that we can easily integrate into the cloud and into the source code management system. So for example, we use GitOps principles with Flux or Argo CD, and with that we get the ability to sync the source control management system with the Kubernetes cluster in real time. Then we have an operator, Crossplane, for example, that really integrates tightly into the cloud platform. So Crossplane gives us the ability to create cloud-native resources like S3 buckets, DynamoDBs, and stuff like that, straight in a Kubernetes native way, very easily. I mentioned it in my title that we also do some AI integration. So with the Amazon Bedrock service, we can utilize large language models like Claude Sonnet 4 and other models that we can integrate so that simple API calls or cross-plane compositions can talk to Amazon Bedrock and bring AI superpowers to your applications. With Kate's GPT, we got a tool that we can help troubleshooting with large language models with AI infusion really easily. On the left-hand side, we see a place where we can store the containers, Amazon ECR, a container registry, and of course we need to build the applications with CI pipelines, so that could be done in GitLab or GitHub Actions, so where we build, test, and scan the applications very easily. Of course, the developers, they need an IDE, so Visual Studio Code or JetBrains or anything like that, with the coding assistant included, like Amazon Q Developer could really help here to create code, review code very easily with that combination. They need to store all the code that we create, for example, in GitLab again, so that we host the code, the application source code. And of course, everything that we build is built in code with Tofu or Terraform, so that we can have the infrastructure as code, everything set up completely as well in code. Some automations, for example, with Helm or Ansible, if that is required, can be put in as well as the platform source code. And then as a developer portal, Backstage, for example, the classic developer portal that could be used, or some of the things can also be run with the AWS Service Catalog to expose some of the features of the platform in an easy to use user interface. Now let's dive a bit deeper into GitOps. What is GitOps? So with GitOps, it's an evolution of DevOps. We have the ability to link source control management and the Kubernetes cluster it's very closely together. So with Flux, for example, or with Argo CD, it doesn't really matter, both are doing more or less the same. We get the ability to have the continuous deployment pipeline actually replaced with an operator that can do these things for us. So if a developer commits something into the source control management system, it starts to build, test, and scan, and then the controller picks it up, deploys it to the Kubernetes cluster on the right-hand side, so that we have everything properly deployed, observed, and operated and fixed in real time. This creates like an immutability firewall for us, so that that everything that is committed is automatically deployed. And these reconciliation loops that run all the time make sure that source control management and the Kubernetes cluster are totally in sync. And that is not only if you commit something, also if you change something manually on the Kubernetes cluster, the operator will override that and make sure that that source control management and Kubernetes are always totally in sync. That creates for you something like an immutability firewall. So with that, you are 100% sure that only what is in Git is also on the Kubernetes cluster, and you can actually remove, for a lot of DevOps people, the admin cluster permissions from the cluster, because only Flux or Argo CD need these permissions, and all the rest is coming from manifests written in code. You can also make your Kubernetes clusters private because with that GitOps model, you change into a pull model. You pull, so the action is initiated from the cluster itself, and you don't need to have your clusters anymore in a public area. So now let's do a short demonstration. In that short demonstration, I show you how actually GitOps is running. So on the right hand side, we have the Kubernetes cluster. On the left hand side, I have my console, and I actually create a Helm chart, a Helm release, a Helm repo. I commit that into my repository. I push it, and within a few seconds, maybe a couple of dozen seconds, it starts to deploy the application onto the Kubernetes cluster. So basically what happens is the Flux that is running on the cluster, you see that here the Flux operator and the controllers, they actually pull the repository all the time, and if they see changes, they go and fetch the Helm release and deploy the Helm release straight onto the Kubernetes cluster. Now I see I have made a mistake I should not have deployed five pods. I only want 2 pods. So I go, I change the values file, I commit and push that again, and within a couple of seconds, that demo is really fast. I sped it up a bit to make it quicker. You see the change that is pushed to the repository will be applied to the cluster itself via the Flux controller. So that happens actually from the customized controllers and from the Helm controllers. They pick up the changes, apply those changes to the cluster, and actually then the change is applied. And now we want to get rid of that application. So we actually delete the manifest from the cluster. We commit and push that. And then as soon as the controller has picked that up, the application is deleted, the resources are freed up, and everything is gone. If you go and change something on the cluster itself, so for example, if you put 10 replicas and change that just with the kubectl command, the Flux controller will pick that up, change it back again to what the value is in the source code management system, so that they are always totally in sync. So you see that demo worked well. We continue to the next area, and that is crossplane. Crossplane is really a cool solution that helps our platform to create cloud-native resources. So with Crossplane, we actually can, in a Kubernetes native way, create resources that you need in the cloud. So for example, S3 buckets or Amazon issues certificates or Route 53 entries. That can all be done very easily with Crossplane. So Crossplane has a controller, and that controller actually provides custom resources on the Kubernetes cluster that then can be triggered via the AWS provider and configured via roles and authentication mechanisms on the cloud platform itself. When you use Crossplane, you actually create custom resources with compositions, for example, that have multiple resources, multiple objects that you use. So what you can do is you can have an ACM certificate, a Route 53 entry, an ingress object, all networking related things configured together, and kick that in with a very simple command. So let's look at that. So in this demonstration, we do have, again, a Kubernetes cluster. As before, we have up here, we do have a certificate monitor. So here we show the certificates that are actually running inside of the cluster. So I'm doing now a change. I add a manifest that will add a new composition. And that manifest that I add is actually deployed via Flux. And that manifest is actually then adding a crossplane composition. So that crossplane composition is called Route 53 ACM ingresses because it consists of these 3 objects. And these 3 objects, as soon as Flux has deployed it, will create a Route 53 record, actually 2, you see that later on, a certificate and an ingress object. So 2 things are coming out of the Kubernetes, out of the cloud provider, the AWS provider, and 1 is coming out of the Kubernetes provider. So here you see the composition has been initiated, and a couple of seconds later you see a new certificate is actually created on the left-hand side on the cloud platform. So you see it's also pending validation, and for that we need to put in Route 53 records, and the composition is doing that as well. So with the composition, we actually have a two-way communication between the cloud platform and the Kubernetes cluster, and we can reuse some of the values to put that in the Kubernetes cluster. So it's a duplex communication, and that really helps. Here you see also an ingress object is created that creates at the end a load balancer, and that load balancer will be injected with the AWS certificate. So we do have a certificate, a load balancer, DNS record, all of it configured with one simple manifest, one simple call, which is only a few lines long. So now we are going to delete that one. So we don't need that anymore. So you see on the left-hand side that we still got 2 certificates running. But in the next command that I issued, I actually removed that composition, and that removal of the composition will as soon start as Flux has kicked in and actually starts to remove the composition, and that starts then to remove the Route 53 record. So here you see it has come in, the composition is gone, and on the left-hand side you see that the certificate is deleted as well. So the ACM cert on AWS is gone too. And that all managed by Flux with source code management system. Now I'm showing you we have also changed the replica count of the WordPress, and up on the WordPress monitor you see it actually changes from a 503 error to the text that is actually visible on the blog itself, which is Cloud Native Zurich 2025. So you have seen now an end-to-end demonstration of crossplane, of Flux, of WordPress, all running at the same time, and actually bringing a new application to our environment. Now, if you have such a great platform where your developers can so easily deploy new applications, they start to use those capabilities. And those capabilities are used and need to be managed. So if you need to provide enough capacity that all those capabilities that are there can be not overrun the platform. So for that we need an elastic infrastructure. So we want to find solutions so that we can auto-scale, compute, databases, search and caching at the same time. So let's look first at compute. So with compute, we had for a long time the ability to use auto-scaling. So with auto-scaling, we have the ability to launch new instances, for example, time-based, remove these instances time-based, or we can do that in a dynamic way with, for example, measuring the CPU utilization and add instances into the auto-scaling group based on these CPU utilizations. Can be connections and memories and other things that you can add depending on how bound your application is. Autoscaling is good, but it is slow. And that slowness is not good for Kubernetes because actually it takes about 5 to 10 minutes to launch new EC2 instances into a Kubernetes cluster with autoscaling, and that's not fast enough. So for Kubernetes, we do have a much better autoscaler available with Carpenter. So with Carpenter, actually, we have a Kubernetes native way of measuring the load that is running on the cluster itself, and then actually request more nodes out of the infrastructure and add it to the fleet. So Carpenter is actually monitoring pending pods and then scales according to the resource requirements that are there. So when Carpenter detects pending pods, it actually goes out and talks to the AWS API to see what is the cheapest, best available instance available to satisfy the resource requirements of these pending pods. It does that with node pools and node classes to actually bring new capacity into the cluster in a very fast way. So you have heard that auto-scaling groups takes about 10 minutes to launch. With Carpenter, we can launch new capacity roughly in 1 minute, within 1 minute. Let me demonstrate that to you, how that actually works. Right-hand side, a cluster, left-hand side, 2 things that we have. We have a console and we do have a node monitor. So right now we have a cluster. All these pods are running on one single node. So you see we don't have any pending pods. So in that demonstration, I'm going to launch a new deployment manifest into the cluster, and that manifest requires for each pod 1 CPU, and I scale it up to 20 replicas. So you have seen there within a second or so, Carpenter picked up that resource request, these pending pods, and actually launched a new node into the cluster really quickly. So within a second, the request was sent to the AWS API, and the new instance is provisioning and is now inserting into the cluster to satisfy these 20 these 20 CPUs. So now you see these pots change from orange to green to blue. That means these pots are now running. These are very simple pots. So they boot up really quickly. So you have seen how quickly it goes. Now we scale down that replica to 0 to show you the opposite direction and how quickly it goes to remove instances as well. So here you see the pots are gone, no more load on the node itself, and within roughly a minute or two, and of course I have sped up that video a bit to not lose too much time, that node is gone and will be deleted. And as you pay with the cloud providers only by the second, you only pay what you really have consumed. So with Carpenter, you actually get the best of it. So you get spot instances because Carpenter is so clever that it is AC aware, storage aware, and also architecture aware, and launches the right instance for you into the right availability zone with the right architecture within a couple of seconds. So roughly 1 minute after a pending pod is here, the pod boots up and is satisfied. This is great for jobs, batch things, but also for 12-factor apps that can really work well with spot instances. Now we have seen how great we can scale the compute side of a Kubernetes cluster. Now let's look at the databases. How do we scale databases? Aurora Serverless v2 has been released about 2.5 years ago, maybe 3 years ago, and that actually allows us now to really auto-scale compute and storage at the same time. Storage scaling was released about 8 or 9 years ago when the first version of Aurora came out. So storage scaling for capacity and for I/O was available since a long time. But since Serverless v2, Aurora Serverless v2, we have fantastic compute auto-scaling as well, because now storage and compute are fully decoupled and compute is fully elastic. Now, how is that working? So AWS has a technology called Caspian, and with Caspian they can hot add CPU and memory into these compute instances depending on the load that is happening. So if it requires more CPU, more memory, if there is a high query demand, high capacity demand, Aurora Serverless v2 scales up and down really quickly. Within roughly 100 milliseconds of the demand that is there on the database starts to scale. Let me show that you in another demonstration how that works. So here we got the cluster on the right hand side. We got the Aurora cluster in serverless v2 mode, and you see it has configured one capacity unit, which is roughly one CPU and 2 GB of memory running. Now we run some commands to actually stress test that Aurora Serverless v2. We use a tool called sysbench, and with sysbench we actually create first tables, so writing operations, then we put records into these tables, and that actually creates already some massive load on the cluster. So you see it has scaled up within seconds to 10 capacity units, so 10 CPUs and 20 GB of RAM without doing anything. And now we actually start to query the database with 1,000 threads, and here you see it scales up instantly to 20 compute capacities, and that is 20 CPUs and 40 GB of RAM. And you also see it fluctuates. So if the load is not as high as before, it also starts to downscale. Downscaling is a bit slower than upscaling because there it needs to find a slot to switch over. But upscaling is 100 milliseconds and it really reacts super fast to it. So here you have seen a demonstration of how you can create a fully elastic setup for MySQL or Postgres in a way that really works super great. Perfect user experience because these queries and write operations will be very fast, and it actually releases you from doing any capacity management. The only thing that you need to manage is the budget, how much you would like to pay for that setup. The same technology is also available for Redis, Memcache, serverless, Kafka, and many more solutions that are fully available. As mentioned before, it's all based on Caspian, and Caspian actually adds CPU memory into the cluster and can also remove that. all based on the Nitro hypervisor technology. And now AWS has actually adapted that Caspian technology to many open source technologies to bring you full elasticity to your AWS services that require them. Good, and now we're coming to the last part of my demonstrations, and that is actually how do you troubleshoot issues on your cluster. If you build a platform with many different operators and things that you put onto the cluster, it really becomes hard to troubleshoot. So you all have worked with Kubernetes before. You know how cool Kubernetes is, but the complexity is certainly there. So here you see a chart, how a troubleshooting workflow, a diagram would look like if something is not working as it should. So, and I'm pretty sure you have troubleshooted some things already and spent hours and hours and hours on searching for solutions, because there are so many events, so many status things that you need to look at, and you need to correlate so much information, it really becomes hard. When I set up all these demonstrations, I used quite a few tools, as you have seen, and getting them all to work was not easy. But I had the help of KateGPT, and KateGPT really helped me to correlate and find the missing pieces. And that was done with the help of large language models. So in the past, before KateGPT, when you had a problem and you did not know what to do, you basically took the event, put it into ChatGPT, and you got an answer out of that. And then you read that, then you tried to correlate what could go wrong. Then you started to look for other solutions. Maybe you got a good hint from ChatGPT. Now with KateGPT, we combine the Kubernetes intelligence, the troubleshooting intelligence, and the large language models into one solution. So you have these analyzers available, and these analyzers are, for example, for pods, deployment, security, storage, many other tools which you see later on that can analyze issues on your cluster, collect events and status and more information, and send that information to, for example, AWS Bedrock with Cloud Sonnet 4.0 to analyze it. So heaps of information is collected, compressed together, sent to the Bedrock service. The large language model will crunch through the data and give you some advice back. And that is actually then consumed from you and gives you actionable insights into how you could fix the Kubernetes cluster very easily. So let's look at that in a demonstration, how that works. Right hand side, we got a cluster. Left hand side, we got the console. On the console, I actually first run a command to configure KateGPT. So KateGPT here is not installed as an operator, just operating it on the CLI, really easy. And with KateGPT, we first need to install it. So on a Mac, you do a brew, you tap it, you install it, you put a couple of aliases, really easy. You see that here. Then you need to authenticate it with Bedrock. Of course, you need to have the right credentials for that. On Bedrock, we use the Anthropic Claude 3.7 or Claude Sonnet 4 model. And then we set it as default. And then we say we want to do an analysis. So you see, I have also created a broken pod up here. And that broken pod actually got an issue and is not starting up correctly. So it is stuck in a failing mode. So now I put in a command that is KateGPT analyze and then explain. I want to filter on the pods and the deployments in the namespace broken, and that actually collects the information, sends it to Bedrock, and Bedrock gives an indication what could be wrong. So it sees the deployment should have one replica, but only has one. So there is something wrong with the pod. So the pod is analyzed, and here in the pod we see we got a failed volume mount because the secret is missing. So here we get two commands, and these commands are create a secret and then also restart the pod. So I'm doing that. Here you see the commands, exactly the same commands as CaseGPT has recommended. I put them in, I restart the pod, it becomes green, blue, and all is fine. I run CaseGPT again, and no problems detected anymore. Here you see we also have more integrations available. The tool comes from an AWS guy, so of course we can integrate with AWS for EKS troubleshooting. We can also do proper interesting tools like Giverno and Prometheus and Kata, more filters that we can use so that we can really troubleshoot the cluster in a good way. So that concludes the demonstration on CaseGPT, and I'm sure you have learned something new here, how you can optimize your troubleshooting skills with less copy-pasting between these tools. So that concludes my presentation and demonstration. This time it all worked because it's my own setup that always works. That's also what I have prepared. Thank you so much again for listening to this presentation. If you want to connect with me, here is my LinkedIn QR code. We also have a meetup, the containers on AWS meetup. We host 3 meetups each year. Sign up, you will hear some interesting talks like this on these meetups. We also often have customers there. Come and see us. We also have our YouTube channel with our meetup talks and more demonstrations that we post there. Subscribe to it as well. Some interesting content there too. So that concludes the whole presentation. Thank you so much for listening. I'll talk to you the next time. Thank you, goodbye, and thanks. Cheers.